Hi, we are in Unit 6. We're looking at periodic properties of the elements, and this is the second video. Well, today in class, you guys were mapping out periodic trends of different properties and trying to explain those properties. Well, here's the explanation that most chemists today believe are the reason why for these observed trends. So here we go. First of all, the periodic trend of atomic size. So within each group or each family, the atomic size gets bigger when you go from top to bottom. Well, why would that be? Well, as you go down a family, you're actually adding an entire energy level. So you know the numbers to the left of the periods? Well, what's happening is we are adding, as we go down, an energy level. And so we're adding a whole new layer to our atom. It's almost like adding a story onto a building. So like you have 2 floors and then you add the 3rd floor and 4th floor and whatever. So that's kind of what's happening as you're going down in a group or a family. You're adding energy levels, and so the atom size is increasing. So they get bigger as you go down. How about when you go across a period from left to right? So here we're not adding any energy levels. The principal quantum number is staying the same. But the atomic size is actually going down. And it's kind of counterintuitive. As we go across a period, we're adding protons to the nucleus. We're adding electrons to the atom. You would think it would get bigger because we're adding stuff. Actually, what we're doing is we're adding positive protons to the nucleus. And we are adding electrons, but we're not giving those electrons any more space. So what's happening is that additional positive charge in the nucleus is pulling in those electrons tighter, and so that is why the size decreases. So as we go across a period, atomic size decreases because of the extra positive charge in the nucleus, with no additional energy level added for those electrons. There's something called the effective nuclear charge that we talked about in the last video, or Z effective. And again, that is not the full nuclear charge that those electrons are feeling in the valence shell, because some of that positive charge is being shielded by these kernel electrons. All right, so let's go ahead and practice. Let's arrange these following atoms in order of increasing size. So you need a periodic table to look at. And so on your periodic table, it would look like this. We would have oxygen, and then fluorine would be to its right. They would be in the same family, in the same period, and sulfur is in the same family as oxygen. So it would be like this. Okay, so the largest one is going to be sulfur. So sulfur is by far the largest, and the reason that it's the largest is because it's farther down on the periodic table, and when you go down, you've added an energy level, it wins. It's the biggest. Okay, now between oxygen and fluorine, when we go across a period, the atomic size gets smaller because we've added protons in the nucleus, and that's pulling those electrons in more tightly. So fluorine is the smallest, and then there's oxygen, and then there's sulfur. These are the types of questions you're going to be asked. This is how we're going to apply these different trends that we've learned in class. All right, let's look at sodium, beryllium, and magnesium. So on the periodic table, beryllium is going to be up here. Magnesium is in the same family as beryllium, and then sodium is over here to the left. So hopefully you have a periodic table in front of you and you can see this arrangement. Okay, so the smallest is going to be beryllium because it has the least amount of energy levels, so it's the smallest. Now, between sodium and magnesium, let's see. As we go across, it gets smaller because we're adding more protons in the nucleus. So magnesium is smaller than our sodium. We're going to be practicing this in class as well. All right, ionization energy. Remember, ionization energy is the amount of energy required to remove an electron. So we're taking away an electron. It always takes energy. it's really a measure of how tightly those electrons are being held. If the electrons are held really tightly, it's going to take a lot of energy to pop them off. Okay, well, the first ionization energy is called I1, and then to remove the second electron, it's called I2, and the third ionization energy to remove the third electron is called I3. And so we know this general trend from our last video, but it's worth repeating. The first ionization energy is always the smallest compared to the second ionization energy. It's going to take more energy to take that second electron away because we've already removed one and it has a positive charge. And then, you know, you see the pattern. To remove the third electron would take even more energy. All right. But now what about ionization energy in terms of the periodic trend? Well, it is going to depend on that effective nuclear charge. That's how tightly the electrons are being held. And it's also going to depend on how far away the electron is from the nucleus. So you can imagine if the electron is farther away from that positive nucleus, it's going to be easier to take away. So we wouldn't need as much energy to take it away. Ionization energy would be lower. All right, so as you go down the periodic trend, the ionization energy decreases. And that's because the electrons are just farther away from that nucleus. All right, but as we go across a period, now the electrons are still in the same energy level as we're going across, but what's happening is they're more tightly held because we're putting more protons in the nucleus. So as you go across a period, the ionization energy generally increases. There are a few exceptions to this trend, but we're not going to worry about them just now. So why does the ionization energy go up? Well, the effective nuclear charge goes up as we go across a period, and our atomic size is also going down. So those electrons that we're trying to take away are closer to the nucleus that has more positive things in it, so they're being more tightly held. Ionization energy is greater. All right, so here we go. Let's pick the one with the highest ionization energy in this question. And so, of course, I hope you have a periodic table that you can be looking at. So this is the arrangement. We're going to have, let's see, on the periodic table, it would be sulfur, then we'd have a chlorine. Selenium would be in the same family as sulfur, and then bromine is below chlorine. All right, so these guys that are down here, they are going to be easier to take the electrons away. So these are going to have the lowest ionization energies because they're farther from the nucleus, the electrons that we're taking. All right, so then let's come up here, sulfur and chlorine. The ionization energy is going to be greatest for chlorine, and the reason is the effective nuclear charge is greater for chlorine, as well as the atomic size is smaller in chlorine than it is for sulfur. All right, so here we go. We're going to try it again, but this time you just have to read the question carefully. We're looking for the lowest ionization energy. And so looking at your periodic table, we've got boron, we've got aluminum, we've got carbon, and we've got silicon. Okay, so the lowest ionization energy, the one that's easiest to take the electron away from. Well, it's going to be in this energy level because they're farther from the nucleus. So would it be silicon or would it be aluminum? And it's going to have the lowest ionization energy is going to be aluminum because there are less protons in the nucleus than there are in silicon, and it's just easier to take that electron away from aluminum. All right, electronegativity. The definition is the ability of an atom, and that's when it's combined with another atom, to attract electrons to itself. And fluorine has the highest electronegativity of 4.0. It really does not want to have electrons taken away. It really wants to attract electrons to itself. And so it has the highest electronegativity. And alkali metals, they really don't care about attracting electrons to themselves, so they have a low electronegativity. And here's the general trend. I just say, hey, remember, fluorine has the highest electronegativity. So the trend is, as you go from left to right across the periodic table, electronegativity increases, and when you go up the periodic table, electronegativity increases. And again, this is because of the attraction to the positive nucleus. All right, now we're going to talk about the radius of ions, comparing them to the radius of their parent atom. So here we've got sodium, and we have sodium where it has a positive 1 charge. So it has lost an electron. Cations are always smaller than their parent, and we're going to find out why in the next slide. Here we have chlorine, and chlorine likes to gain electrons to form the chloride ion with a negative 1 charge. And notice that it's larger than the chlorine atom. So why are cations smaller? Well, when you remove an electron, a lot of times you're losing an entire valence shell. So when you lose a shell, of course, the atom is going to be smaller now. So cations are always smaller than the parent where they came from. And the anions are always larger. Well, why is that? Well, remember, we're adding electrons to form an anion. We're putting electrons into a cloud of electrons that's negatively charged. We're adding a negative to a negative, and we know that like charges repel one another. And so those like charges are going to be pushing apart, and the anion is going to be larger because of what we call electron repulsion. So anions are larger than the atom that they came from, and cations are smaller. And finally, the last trend is in metallic character, and we know that the metals are on the left side of the periodic table. So the left side of the periodic table are metals, the right are nonmetals, and so the metallic character is going to decrease as we go from left to right across a period. But the as you go down the periodic table, the metallic character increases. And so the lower left corner of the periodic table are where you would find the most metallic elements. The upper right-hand corner of the periodic table is where you would find elements with the most non-metallic characteristics. Okay, that's it. And so we will see you tomorrow, and we're going to practice these trends over and over and over. Have a good night.